So in this video, we're going to talk briefly about the various properties of our convolution integral. We're not going to be using these too much. I'll point out sort of when we're doing our graphical interpretation of convolution, I'll point out how one of our properties is applied, but mostly I just want to put these here so that if you're ever working with convolution in the future, you'll at least be aware of some of these general properties. So the first property that we're going to look at is our commutative property. And basically what this is saying is it doesn't matter what order we do our convolution in. So x of t convolved with h of t is equal to h of t convolved with x of t. So either order is going to give us the same result. And so again, thinking back to our integral, that makes sense because these are just two terms within our integral. So our second property is our distributive property. So distributive. And so again, this is going to look similar to what we have for example, multiplication. So if we have f of t being convolved with some sum, which is x of t plus y of t, we can then say that this is equivalent to having f of t convolved with x of t, and then plus f of t convolved with y of t. The next one we're going to look at is our associative property. So associative. And for our associative property, we're saying we have f of t convolved with, and then in brackets we have x of t convolved with y of t. And so I should mention too that in this case our x and our y and f and are all just, and our h even, are all just some general function. They're not necessarily input, output, impulse, response, anything like that. So in this case for our associative property, we're saying it doesn't matter what order we do these convolutions in. So we could also do f of t convolved with x of t first. So we can put that term in brackets, and then convolve that with y of t. So the next properties don't necessarily have names, but let's just take a look at those. So if we have f of t, so these are more specific cases, if we have some function f of t convolved with our impulse, delta of t, well, thinking back to what our integral definition was, that would be negative infinity to infinity for our limits times f of lambda times delta of t minus lambda d lambda, and from here we can see this is essentially our sifting property. So this is just going to equal to f of t. So let me just write down here, this is our sifting property. So a few other sort of similar properties we have here. If we have f of t convolved with a shifted delta, so delta of t minus some value t naught, then that's going to give us f of t minus t naught. So again, that just comes from that sifting property. The next one is if we have f of t convolved with the derivative of our impulse function, so delta prime of t, then that's just going to give us f prime of t. And then the final property we're going to consider here is what if we convolve some function f of t with our unit step function, so u of t, and if we go back and we think about our integral again, we can say this is the integral from negative infinity to infinity of f of lambda times u of t minus lambda d lambda. Well, what that's going to do is we're basically just setting our upper limit to t. So we can say this then becomes the integral from negative infinity to t of f of lambda d lambda. So basically that u of t is just setting where our function is on, essentially. So in the next video, we're going to come back and we're going to simplify our integral expression for convolution. And then we're going to take a closer look at why we even want to deal with convolution with relation to our Laplace transforms and Laplace analysis.